Okay, welcome back everybody. So today is a very short video on leakage and leaky confined aquifers. So here's an illustration on the right hand side, and that's basically when you have a confined unit, right, that have an aquitard on top. So there is some communication between, an overlaying aquifer that can be another confining or another confined aquifer, or that can be an unconfined aquifer, up top, and a confined aquifer at the bottom. Imagine that if this, if this unit here, the aquitard, has some conductivity, hydraulic conductivity, then let's say you're pumping right into that confined unit. Obviously, if you're dropping the head here, you're going to vacuum, water from that overlaying aquifer, which may or may not be desirable, right? So let's say that top unit is an unconfined aquifer that gets polluted from some surface accumulation of some contamination. Now we have a problem because now we're pumping that water in, right? So again, remember this Boussinesq equation from last lecture. So this is the time changing one. Now here, what we're looking at basically is a case where, so similar to the recharge and divide lecture a couple lectures back, right? Where we have now leakage, but because it's a confined aquifer, right, we won't have to worry about that square business, and we can just solve it a little simpler. So again, remember that dq prime dx equals, so 0. In this case, it's not 0, it's actually something. And now we have to figure out what that something else. So that something is that recharge, from, now instead of rain, it's that recharge from that leaking unit, that aquitard. Okay, so let's call it, something different. Let's call it E, right? If we look at the units, again, we can put it in the unsteady, if you will, in the time varying, Boussinesq equation, complete equation. Again, if we assume, I said last time, that H is B, right, for a confined aquifer, this is always true. So now we get to our, basic equation, again, the Boussinesq equation with now E over T, right? Remember that T comes from the left-hand side and goes to the right-hand side, so that's why it's carried here. Now the question is, what is E, or what units are E? Well, it's just the same as W, right? So if you look at here, right, we can just call this E. This is T here for the steady state one. So E is just the same units as W. So if you remember, it's just the units of rain or the units of Darcy flux in this case, right? So units are length per time. And I'm sorry, this is going blurry. Okay, so we have the leakage across that's in length per time, which is basically the Darcy flux, right? The little Q, the Darcy flux across that aquitard. So what's leaking is Darcy. So we can write it as literally a Darcy flux across this aquitard. So if we do this, right, this is what you have here. So if we write the leakage across the aquitard as the Darcy flux across that aquitard, you can see that now we have a K prime, which is basically the hydraulic conductivity, the, presumably small, low conductivity of that aquitard, but it's there because it's leaking. And then the head difference across the aquitard divided by its own width, right? So B prime would be the width of the aquitard. H0 and H are the heads, across it, so right at the top and right at the bottom of it. And then K prime is its own hydraulic conductivity. So you can see how that leakage across the aquitard is just the Darcy flux across the aquitard. And this is how we deal with the leakage from leaky confined aquifer. Again, when we do the lectures on wells, on hydraulics of wells, we'll talk about those situations a little more. All right, I think this is it for today. Thank you.